Hi, I'm Jnana, a third year PhD candidate advised by Professor Jagana, and we're from the University of Minnesota Twin Cities. Today I'll be talking about some work that we've done on industrial demand response with interruptible load in collaboration with Satyajit Amaran from Dow. The key motivation for demand response is volatility in electricity pricing. Here I show a plot of electricity prices from one region in the state of Texas, and we see that there is huge variation in prices across time. This volatility in prices is only expected to increase as more renewable energy sources are used to produce electricity. Chemical industries are large electricity consumers, and this is also expected to increase as we're trying to shift from fossil fuels to cleaner energy sources. This is where demand response strategies can be very helpful, where we as electricity consumers actively react to volatility in electricity prices by adjusting our consumption. With this in mind, our industrial collaborator Dow wanted to look at strategies to reduce costs in their carbon capture facility. Here, flue gas containing CO2 is passed through a scrubber where it is absorbed by a solvent. This CO2-rich solvent is then sent through a stripper where concentrated CO2 is dissolved. This CO2 is then sent through a train of compressors where it is converted to a pressure that is suitable for sequestration or further utilization. The compressor train is the highest consumer of electricity in the facility, and since electricity is expensive, it accounts for a big portion of the facility's operating costs. So our goal was to apply demand response strategies to reduce costs by leveraging operational flexibility. However, since this part of the plant pretty much runs at a steady state, we cannot vary the input flow rate into the compressors. So we needed to find a way to flexibly operate the compressor train. To do that, we proposed introducing two storage tanks, one at the beginning of the compressor train and another in between compressors 2 and 3. To give you an idea, the size of tank 1 is less than 2 time periods worth of CO2, and the size of tank 2 is less than 4 time periods worth. We write a general optimization model for scheduling that we've applied on this compressor train, where we minimize the electricity costs, which is a function of our scheduling decisions, which we denote here by X, and these scheduling decisions are constrained by the feasible operating regions, which in the compressor train case study are limits on the capacity. And we have transition constraints which ensure practical switching between different operating modes, like off, startup, and on. And finally, we have mass balance and initial conditions to complete the problem. We solve this model for a 24-hour scheduling horizon, and we use electricity prices from Texas, which are shown here on the right y-axis in black. And on the left y-axis, we have electricity consumption, which for compressors 3 to 5 turns out like this for this day. Here we see that compressors are shut down when the electricity prices are high, which makes intuitive sense. And there is a small amount of electricity consumption in time period 8 here, which comes because of our transition constraints that require an hour of startup time before the compressors can be turned on again. However, we don't see a similar shutting down of compressors 1 and 2, and this is because of the choice of the size of tank 1 that we made, which is simply not big enough to allow for compressor shutdown. So this was a demonstration of how demand response under time-sensitive pricing looks like. We save money by not running some of our compressors in during these high price time periods. This is also favorable for the electricity grid because typically high prices correlate with high power demand. So to encourage demand response, the electricity markets run reserve markets where operational flexibility can be traded. One of the key motivations for grid operators to run reserve markets is balancing supply and demand. Let's say due to some contingency, supply falls short. One solution is to use backup generators to satisfy the demand. This, however, is expensive as the grid now needs to maintain these backup generators which can produce electricity at a short notice. But another alternate is to ask the electricity consumers to reduce their demand in exchange for some incentives. This is referred to as providing interruptible load, and it's less expensive for the grid than backup generators. If we do decide to provide interruptible load, then we decide on the amount of interruptible load that we want to provide and our nominal power consumption ahead of the scheduling horizon. So these become our first stage variables. And on the day of the operation, let's say we're asked to reduce our load during these time periods, then the curve in red shown here is the actual power consumption that we end up with. This is why I call the first stage decision variables as nominal power consumption, because this will be our consumption profile if no load reduction was made. Now, one nice thing about providing interruptible load is that payment is made regardless of how much load reduction is requested. So in the best case, we get paid for providing interruptible load in all these time periods and still end up with our nominal power consumption where we don't have to change anything in our schedule. But the challenge is that the load reduction requests are uncertain, and uh, to account for that, we go back to our scheduling model and rewrite the model to include interruptible load provision. First, the objective is modified to include revenue from interruptible load, and our scheduling decisions now will depend on load reduction requests up to time period T. This is because, say, we're asked to reduce our load in the first time period, then to make up for the lost production in the first time period, we have to increase our production later. So for this to happen, we need to model our decision variables as function of uncertain parameters up to time t and not just time t. And then we have similar constraints as before with additional interruptible load constraints which can come from any rules the reserve market may have. And finally, we need all of these constraints to be satisfied for all possible values of load reduction requests. Some key features of these load reduction requests are that they have to be satisfied, or else heavy penalties may be levied, or in some cases, we could be removed from the reserve market. And the other thing is that the underlying probability distributions are hard to determine for this uncertainty. So, keeping this in mind, we decided to take a robust optimization approach. And the first steps in taking in a robust optimization approach is answering the question of what possible values can the uncertain parameter take. And the second question is how do we want to relate the decision variables with our uncertain parameters? To answer the first question, we essentially need to model our uncertainty set. An intuitive approach would be to say that load reduction requests in each time period t can take a value between 0 and the amount of interruptible load that we've committed to. However, this is an uncertainty set that depends on our first stage decision variable, which will make our problem harder. But a simple workaround is to define a normalized load reduction WT, which will remove the decision dependence from the uncertainty set. Now, for this uncertainty set, whenever WT takes a non-zero value, a load reduction request has happened. So if we plot the cumulative load reduction requests with respect to time, the plot will look something like this in the worst case. So up to 24 load reduction requests can happen in a span of 24 hours. This, however, is very conservative because load reduction requests are only made during contingencies, and the grid operator has multiple interruptible load providers at their disposal. So to reduce conservatism, we modify our uncertainty set by setting the cumulative load reduction requests to something like this. Here we assume that load reduction requests can happen once in the first 8 time periods, twice in the first 16 time periods, and so on. This is called a budget of uncertainty approach and mathematically looks something like this. Now we move to the second question where we want to relate our uncertain parameters and the decision variables. Previous works have considered affine decision rules which look something like this. Here, the decision variable is written as the sum of a nominal decision and a recourse decision, where the recourse decision has a linear dependence on the uncertain parameter. One obvious drawback of this simple affine decision rule is that it cannot accommodate discrete variables. And another not so obvious drawback is that we cannot explore recourse in continuous variables fully. For example, consider the flow rate through a compressor. Let's say in the nominal case, the flow rate runs at full capacity, and and uh, as the normalized load reduction value increases, we would want to reduce the flow rate through the compressor so that we can decrease our electricity consumption to satisfy the request. But once we reach the minimum flow rate, the only option is to shut down the compressor to allow for higher load reduction requests. So if this piecewise linearity was not possible, then we will only be able to provide interruptible load from reducing the flow rate, but not from shutting down the compressor. So the main contribution of our work is that we use piecewise linear affine decision rules, which I will explain soon, as compared to previous works where simple affine decision rules were used. So to achieve piecewise linearity, we introduce breakpoints in the uncertainty set, which, as you can probably guess, are partially inspired by the breaks that we see in this flow rate plot. To explain the structure of our piecewise linear decision rules, I take the example of the uncertainty set for a single time period with a single breakpoint. And first, to cater discrete variables, we define them as sum of the nominal decision and the recourse decision, with the recourse coefficient now multiplying a lifted vector w hat. Since we only have one breakpoint in our problem, w hat only has one component, which takes the value 1 when w is greater than the breakpoint value. So with this decision rule, say we want to model a variable that takes the value 1 if the compressor is on and 0 otherwise. Then in the nominal case, the x dot will be 1, and if we choose x hat to be -1, then this allows this discrete variable to become 0 when the normalized load reduction request is higher than the breakpoint value. So this allows for discrete recourse, which is what we were trying to achieve. But one thing to note here is that x dot and x hats also need to be integer variables. So using these decision rules increases the number of discrete variables in our problem, which has an effect on the computation time. Next, to achieve piecewise linearity in continuous variables, we again write them as the sum of a nominal decision and the recourse decision. But the recourse decision now has two lifted vectors, with w hat being the same as before. And the w bar, since we have two pieces in our uncertainty set now, has two components, which look something like this. The structure of these of w bar's components is such that if we choose x bar to be just a multiple of a vector of ones, then we will just end up with the simple affine decision rules we saw in the previous slide. As an example, let's say we want to construct this dependence of flow rate on the uncertain parameter, then these would be the the recourse coefficients that we would choose. Uh, when when wt is 0, that is in the nominal case, x dot would be f max, and between 0 and the breakpoint here, we have a simple line which is reflected in the x bar here, where it just takes the value of the slope. And in the second piece of our uncertainty set, we see that the flow rate is simply 0. So the second component of the x bar simply takes the value 0. And at the breakpoint, we want the flow rate to go from f min to 0. So we chose x hat to be negative of f min so that the value becomes 0 once wt is greater than the breakpoint value. Now that we've answered the two questions that we've posed initially, we have the required pieces for robust optimization in place. So we simply substitute the decision rules with the lifted uncertain parameters into the model, and then we also lift our uncertainty set uh, to the new lifted uncertain parameter space. And then we apply robust optimization techniques to arrive at a tractable MILP, which we apply on our compressor train case study. Here we compare three cases, and the first case is where we choose not to provide any interruptible load, and this is same as the scheduling under time-sensitive pricing problem we saw towards the beginning of the presentation. Next, we have the case where only continuous recourse is allowed, and this is similar to what previous works have done. Here I use a two-axis plot again uh, to show the results, and on the right we have prices, uh, which and for now I just show the electricity prices in black, and on the left we have the electricity requirement with the nominal electricity consumption shown in blue, and we see that the nominal electricity consumption takes lower values when the electricity price is high, which is something that we've seen before. Now I show the values related to interruptible load provision with the interruptible load price in red. So this is the price that the electricity market will pay us for providing interruptible load. And then green and corresponding to the left y-axis is the amount of interruptible load that we decided to provide. And we see that a model tries to provide more interruptible load when there is a peak in the interruptible load pricing so that we get paid more, uh, which is what we would expect. And the same plot with our first stage variables for mixed integer recourse looks something like this. And the first thing that we immediately notice is that the amount of interruptible load that we provide is much higher. And this is because with mixed integer recourse, we know we can shut down our compressors even if a large amount of load reduction request has been made. So this reflects in the revenue that this revenue from interruptible load is reflected in the cost reduction values that we see. And but however, since mixed integer recourse, there are a lot of new integer variables that we introduce into the model. So the effect of that is seen on the computation time, with the mixed integer recourse in this case taking a little under 2 hours to solve the problem. I just like to note here that this is still practical because we'll be solving this problem once every day, and we will know the electricity and the interruptible load prices well in advance for us to run the problem and get the results. Next, I show how recourse decisions have been made in our mixed integer recourse case for one particular scenario of load reduction requests. On the right y-axis, I again have electricity and interruptible load prices, and on the left is electricity consumption, which in the nominal case looks something like this. And say we were made load reduction requests in these three time periods, then the recourse decisions that we need to make for compressors 3 to 5 looks something like this. As you can tell, the magnitude of load reduction requests in time period 18 is high, so we have to shut down our compressors 3 to 5 to satisfy that request. But once we shut down, we again need an hour to start our compressors back up. So that is also reflected in our recourse decisions that our model predicts. Similar recourse decisions which make practical sense are also made for compressors 1 to 2. Now that we've seen a mixed integer recourse as the potential to reduce operating costs, we wanted to see what happens if we move our second storage tank across the compressor chain. We fix the volume of the tank so as the tank 2 moves down the compressor train, it can hold more amounts of CO2 as now CO2 is at a higher pressure. We find that for the size of storage tanks that we chose, the minimal operating costs do occur when tank 2 is between compressors 2 and 3. To understand why this happens, let's look at the first case where when the tank is placed between compressors 1 and 2. In this case, the size of storage tank 2 is simply not uh, big enough to allow the shutdown of compressors 2 to 5. So we cannot provide a lot of interruptible load, and consequently we don't get a lot of revenue from it. On the other extreme, when the storage tank 2 is placed in between compressors 4 and 5, uh, we again have higher costs, and this is because now compressors 1 to 4 do not have significant operational flexibility, which can allow them to provide more interruptible load. So we find that the design choices that we make for these tanks also play a huge role in terms of the amount of interruptible load we can provide. So to summarize, hopefully I've convinced you today that providing interruptible load is a good idea for reducing electricity costs in power-intensive plants. This is also helpful for the electricity grid stability, so the grid operator would also be grateful if you do it. And if you do decide to provide interruptible load, then a robust optimization approach with mixed integer recourse is a good option as it will allow you to fully exploit the operational flexibility in your processes. Lastly, we also saw that the design choices that we make also affect the amount of interruptible load we can provide. So as part of our future work, we plan to explore this design problem systematically. And that is all I have for today. Thank you for listening.